Greetings. Time to finish up our chapter on triple integrals by talking about how to convert them into different coordinate systems, specifically cylindrical and spherical coordinates. So triple integrals, don't forget, are integrals that are actually adding up things in 3 different dimensions simultaneously, and therefore I have the availability of using cylindrical or spherical coordinates because those are both 3D systems as well as our XYZ coordinate system. Okay, so remember polar, we did that for double integrals. That was an alternate way of writing our double integrals, right? And we got an r d theta because it was the arc length r d theta and then the normal differential dr. Spherical, cylindrical coordinates are not much different than polar because cylindrical are still the same kind of polar direction in the plane, but then you still have the z direction to make the cylindrical solidify there. Okay, so if you think about polar coordinates, cylindrical is really just incorporating the z coordinate with the r and theta that already take care of the xy plane. So that's why we still have the r dr d theta from the polar coordinates, and then you also have dz. And then that's how you would actually convert the differential portion of your integral, of your triple integral. Okay, and then of course you would want to rewrite your function in terms of r theta and z, and then your boundaries of course would have to be written in that same sense. Okay, now spherical coordinates, it's a little bit different than cylindrical. With spherical coordinates, don't forget the x, y, and z all have these relationships with rho, theta, and phi, right? That's our actual transformation between spherical and rectangular coordinates there. Okay, one other added little extra piece, the r, as in the r from cylindrical and polar coordinates, is also one of these things that can be translated into the spherical world, and it's equal to rho times sine phi. And that's because r and z make up that right triangle that rho is the hypotenuse of. Okay, so the r ends up being the sine portion because of where phi is here. R is actually opposite, and z is adjacent, hence why z has the cosine piece there. Okay, so if I'm doing a triple integral in spherical coordinates, I have to remember that what I'm actually doing is 2 different rotations, right? I'm still doing the theta rotation this way, right? That's here, but I'm also doing the phi rotation that's this way. And both of those rotations have to have this same kind of methodology in that the actual differential length is an arc length. So you're going to have the r d theta, just like cylindrical and polar, right? The r d theta is there, but I have to convert that into spherical. So r gives you a rho sine phi d theta. And then also the arc length just in the phi rotation off of the z-axis, right? The radial component of that is rho, and I'm rotating in the phi direction. So the arc length is the rho, the radius d phi, right? So rho d phi there. Therefore, altogether, if you're going to do one of these integrals in spherical coordinates, what you end up with is rho squared sine phi, and then your differential pieces that you can arrange in whatever order your boundaries demand, or whichever ones tickles your fancy at the time. First couple of examples. If you have triple integrals that are already iterated into those current forms, like already in cylindrical form, I can tell because of the dr, d theta, dz, or already in spherical form, right, d rho, d phi, d theta, then there's no converting necessary. You don't need to multiply anything extra with the conversion factors or anything like that. They're already in that format, okay? So this was handed to us and says here, just evaluate this triple integral. what I want you to see is that this is no different than already evaluating a triple integral in the rectangular form, right? It's already in the form. I just need to do the integrals now, right? Through the antiderivative calculus here. Okay, so dr goes first. So this first integral is dr. R is the only thing that corresponds to that. The cosine theta is constant. I can sort of think of that as just coming out right here. So I've got integral from 0 to 3, integral from pi over 6 to pi over 3, and then the antiderivative of just r dr, right? The cosine theta just pulls out, and the antiderivative of r dr is 1/2 r squared. And that's going from 0 to 4. And then I still have d theta dz. Okay, well, 1/2 r squared evaluated from 0 to 4, right? So if I plug in 4 and I plug in 0, right, that's going to be 16 minus 0, or 16. And 1/2 of 16 is just 8, right? This piece right here is just going to give me a value of 8. So next, I'm going to be doing the d theta. See, that's the next shell I have here, the next layer that I have. And I'm just going to be doing the antiderivative of cosine theta d theta, basically. Okay, so then I still have my integral from 0 to 3. dz has no dependence anywhere. I'm just going to pull him front times antiderivative of cosine theta. That's still sine theta, from pi over 6 to pi over 3, times the 8 that we had from that one, right? Okay, so sine of pi over 3, right? Sine of 60 degrees, square root of 3 over 2. And sine of pi over 6 is just 1/2. And then I need to do this antiderivative dz, right? It's just z. So 3 minus 0, basically, which is just going to give me 3. So I've got 3 times, and then I've got square root of 3 over 2 minus 1/2, and then times 8 right here. It'll help us out if we can factor a 1/2 out. Times that 8 will give me a 4, times that 3 will give me a total of 12. And I've got square root of 3 minus 1 there. Right? No difference in once the integral is actually set up, right? We're still just doing it in the same layers like any other triple integral. Okay? Spherical coordinates. Same thing, right? I've got my 3 integrals, the boundaries are already set. Whatever was going on with the function and any other multiplied factors is already simplified here, right? It's set up and ready to go. So I'm doing d rho first, right? Cosine theta has no dependence on that, so I'll just be pulling that forward. Right, that's still there. Cosine theta. And then antiderivative of d rho is all I've got there, right? That's just rho, which is going to give me sine theta minus 0, or just sine theta, right? That's this piece right here. The integral, antiderivative, d rho, just gave me sine theta minus 0. Hence, the sine theta here. All right. We still have d phi d theta. Right? So next layer is to do d phi. But these are both based on theta, so they can really just pull forward again. And I'll have the integral d phi, right? That piece right there is just going to give me phi again, and it's just going to be pi over 2 minus 0. So this integral with this, because both of these guys are going to go out, right, into the theta integral. Here I'm just getting pi over 2 minus 0 again, right? This minus this. Okay. So then let's see, this is equal to integral from 0 to pi over 3, right? I've got the cosine theta, sine theta, and then it's times pi over 2. I'll just put that out front here to get it out of the way, times pi over 2. Well, there's a normal substitution, right? I'll just go ahead and let u equal sine theta, right here. I'll just let u equal sine theta. That means du is going to be cosine theta d theta, which I happen to already have, right? So cosine theta d theta is my substitution. And I'm just integrating basically u, so I get 1/2 u squared. So pi over 2 times 1/2, and that's going to give me sine squared, evaluated from 0 to pi over 3. Sine of pi over 3 is square root of 3 over 2, right? We already saw that a little while ago. Hopefully you've seen it before that too. And sine of 0 is 0. So let's see what I've got now. I've got pi over 2 times the half. And now I've also got square root of 3 over 2 all squared. Let's go ahead and separate that out like this. Minus 0 squared. Okay? So I've got 3 and then 4, right? 3/4 here, times a half times pi over 2. So altogether I've got 3 pi over 16, right? 4 times 4 there. Okay. So again, when the integrals are already set up, no factoring or no multiplication factors are needed or anything like that. They're just ready to go. They just happen to be in the other coordinate system. Next example. I'm going to take this particular situation and we're going to look at it all 3 different systems. Let's start in rectangular, and then we'll also try it in cylindrical, and then we'll also try it in spherical. And then you can get a feeling for how all of those integrals go and which one you may like in certain situations. Okay? So I've got this volume that I want to calculate. So already you should be thinking, oh, we're doing triple integral dv, right? Because that's how we do volumes with triple integrals. You just do the integral with the dv, okay? Not actually adding up any other function inside of the region, just the volume itself, okay? So we know we're going to be doing that. Let's go ahead and write that down and remind ourselves. Over whatever region in 3 space Q is, dv, right? That's what we're going to be doing. Okay, so let's talk about what this is for a second. X squared plus y squared plus z squared equals 36 is a sphere of radius 6. And that's supposed to be the cap. It says it's bounded above by the sphere. Okay, so there must be something else fitting inside of the sphere to do the bottom, right? So it's capped below by 5z equals x squared plus y squared, right? And that's a circular little paraboloid, right? I've got the 5z equals x squared, parabolas in the zx plane, and 5z equals y squared, parabolas in the zy plane. And then, of course, x squared plus y squared is circular in the xy plane. So we've got that paraboloid, right, the circular kind, from underneath. And then you've got a sphere on top, okay? And we're going to compute the volume inside of this object, okay? So it's going to look something like this, right? I've got my parabolas here in the zy plane and my parabolas in the ZX plane. And then I've got my circles, right, in this plane here. So that's the paraboloid from underneath, right? And then it's supposed to be a sphere on top. The sphere has a bigger radius, though, than this guy, right? So look right here. The sphere is radius 6. It's going to be doing this, basically. The axis is going to keep going that way. Right? There's my sphere, where the equator of it is in the plane, right? So what we're looking at is the piece of the sphere cap here, right? Just this piece right here that happens to sit right underneath where the paraboloid is going to come up and intersect the sphere, okay? So we definitely want to find this intersection here, okay? Before we get too deep, why don't you take a look at what this really looks like better than I can draw it. Here are those two equations that we were talking about, the top and the bottom of our volume. Here's the sphere, x squared plus y squared plus z squared equals 36. And here's the paraboloid, 5z equals x squared plus y squared. Now if you look at both of them at the same time, you can see it's just like we were discussing. They do meet in a symmetric way in this circle up at the top. And it's when z equals 4. So you can see the cutoff there with the plane z equals 4, right? So that intersection looks like a circle like this, right? Let me turn off the plane. So there's the circle where they intersect, right? Okay, so let's take a look at just the surfaces then, right? That's where that sphere top is meeting that paraboloid right at that circle. So as we were talking about, right, we're going to be integrating over this region in the circle in here. Let's get a better look of what this thing actually looks like, though, because it's not all of these pieces on the outside, right? Here, instead of this whole sphere, here's the actual top piece right here. Let me turn this sphere off. So there's the top of the sphere there. And then the same thing with the paraboloid bottom, right? There's the paraboloid bottom piece right there. Let me turn off the other paraboloid. So we're actually getting the volume of this symmetric object right here, right? Now when we're doing this in cylindrical, keep in mind that we're just going to be integrating over a polar region here, and I'm still going to be subtracting top minus bottom. When we do this in spherical instead of cylindrical, then I'm going to be integrating a little bit differently. Okay, as you'll see soon, I want you to take a look at what angle phi does in spherical coordinates. Okay, so let me take off the bottom here and just take a look. If I'm in spherical coordinates, the angle phi is the angle off of the z-axis that the radial component rotates in this downward direction from the z-axis down towards the xy plane, right? This is phi, the angle phi that I'm changing in spherical right now. Okay, so the thing to note is, since the spherical integral that we're going to do in a little bit is going to go from the center outward, then it's going to matter which direction my phi is pointing, because I've got two different shapes here, right? So look, take a look at the YZ plane here, right? This is the YZ plane right here. And when phi is anywhere from 0 up until the arc cosine of 2/3, which is right about right here, 0.84.
you can see it's all in the sphere. It actually hits a point in the sphere. But if I go past that point, right, the radial component is going to come through on a point on the paraboloid. Okay, so it's important when we're doing the spherical one later that we actually find the location where my phi angle is pointing at the intersection of these two. And then that ends up being the arc cosine of 2/3. See, as I punch it in there, and it hits it dead on onto the intersection circle there. Okay, so when I'm doing the spherical version, that's where I'll be splitting two different integrals there between 0 to the 0.84, and then from that 0.84 down to pi over 2 for phi. Okay.
So let's set up the rectangular version of this triple integral, right? First and foremost, I need to know where these intersect so that I can get a boundary, right? I need to know exactly this ring right here where they intersect. Okay, fine. I need to know where these two surfaces intersect. I'm just going to set it up where they're equal to each other somehow. Luckily, 5z is equal to x squared plus y squared, right? So I can directly plug that in for x squared plus y squared right here. And what I'm going to get is 5z plus z squared equals 36, right? Well, that's just a quadratic I have to solve in z now. So I'll rearrange it. And then I'll factor it. Right? And then I'll solve for z. Now, z equals -9 means somewhere beneath, right? Z would have to be somewhere down here. Well, that doesn't make sense in either sense, because for one, the paraboloid's facing upward, right? Also, z equals -9 is beyond the radius of the lower part of the sphere. So either way, that answer doesn't make sense. But z equals 4 does make sense. The cap of the sphere up here is at z equals 6. Here's 5 and here's 4. So right at z equals 4 right here, right, is where the paraboloid and the sphere are intersecting. So we're getting that piece of volume in between the two there. Okay? So what we're going to want to do to make this a lot like the integrals rectangular that you're familiar with is we're still going to integrate all of the z heights, right, between these two. So I'm going to set the integral up rectangularly. So that our first integral is dz, right? And then the bottom and then the top. Okay, so the bottom of the z's, remember we're inside of this object, so the bottom z is actually the lower surface. And then the z's go up to the top surface, right? So the bottom of z right here is going to have to be the paraboloid. Solve for z, right? Solving for z here means z is going to be 1/5 x squared plus y squared. So that's what I have as my lower limit here. And then integrating to the upper part, I have to solve for z here, right? So I'll subtract and do a square root. I've got 36 minus x squared minus y squared for that one. And I took the positive square root on that one. Like so. So my z is integrating from the bottom curve to the top curve, right? And it's okay to have x and y dependence as we move further out, right, is when the dependencies need to start breaking away. So next, let's do dy. Okay? Now let's pretend we're going to look over the top of this thing again, just like I showed you in the video, right? You can look over the top of it and see the circle itself, right, that we're integrating over in the xy plane, right? It's going to look like this from over the top. It's like you're looking down the barrel of the paraboloid, right? And the sphere is on the top right here. When z equals 4, what I have is x squared plus y squared is equal to 20. So this is a circle with radius square root of 20. Right? Circle with that kind of radius there. Well, we're doing rectangular, right? So I've got my x direction and my y direction. I've said I'm going to do y next. So I'm going to be integrating y from 0, right, up to the curve. And we can make this a little easier on ourselves. This is a completely symmetric object, right? So I can actually just take a quarter of it right here, just do one corner right here from 0 to here and from 0 to here. These two pieces, just take this corner. And all I'll need to do is multiply a 4 out front because of the symmetry, right? It's spherical and the paraboloid is circular. So we have all that symmetry working for us then, right? Okay, so y is going to go from the axis up to the curve, right? Well, this is the curve right here. Solve for y. It's going to go from 0 up to the square root of 20 minus x squared. And then lastly, x from left to right of that piece is just going to go from 0 to the square root of 20. Okay? So that integral looks extremely unappetizing, doesn't it? Okay? We can go through the first couple of steps here, and I'm going to show you, but at some point, this integral becomes untenable. It really does for most people that just want to do this, you know, either for skill or for leisure, or even if you're just learning. That this really is one of the reasons why we have these other systems to convert into, and that's the point I'm hoping that I'm getting across to you here, right? This first piece of the integral here, just the dz portion, it's going to give you z, and then it's, you know, top minus bottom there. So what you're going to end up with is this square root 36 minus x squared minus y squared minus 1/5 x squared plus y squared. Okay? Whoops. Forgot my dx right here, right? So that next layer, I still am integrating from 0 to square root of 20 minus x squared dy. Okay? So imagine doing all of this integral in terms of y. And then even when you're done with that, you still have one more integral dx. Okay? It becomes very, very gruesome after this point. Very, very chunky. You have to split it up, and you have to do this piece either with trig subs or some other advanced substitution that will land you either in logarithm land or arc sine land, mixed with all of the other polynomial pieces that you get. It becomes extremely large and not advisable, right? At this point, I'm just hoping that you see that it's not worth going through the extra trouble here, because the next couple of versions are actually much, much nicer. Now let's try cylindrical. Remember, cylindrical is basically just polar and z direction added in, right? So really what I'm doing is converting all the x's and the y's into polar form. And then I also happen to have the z variable mixed in with it, right? So if I'm going to do this, right, let's write down, first of all, the same thing as we did before. We know that these two intersect at z equals 4, right? Which causes x squared plus y squared equal to 20 as the intersection curve, right? So that's sort of our boundary there. All right, well, let's go ahead and convert all of these things into polar and cylindrical useful objects, right? This piece right here, x squared plus y squared, is going to be r squared plus z squared equals 36. And this piece right here, I'll have 5z equals r squared. Okay. So we're going to have sort of the same idea as the rectangular one here, except instead of x and y, I'm going to have r and theta for my cylindrical. But I still have my z, which makes it cylindrical, r, theta, and z. I'm still going to have the same scheme. I have the sphere on top, the paraboloid on bottom. I'm going to be integrating in between the two objects to get the volume completely inside. Okay, so for my triple integral, I'm going to label my integrals like this. I'll have the theta, the r, and then the z integrals. Okay, in that order from this direction. Okay, now of course I'm just doing dv, and since this is cylindrical, that's just going to be r dz dr d theta, right? The r d theta, right, is part of the polar, and then I've still got my dz and dr in there. So z is still from bottom curve to top curve, but they've changed into polar form, well, cylindrical form, right? So the bottom curve, the paraboloid, 5z equals r squared. Since it's a z that I'm integrating there, I'll be doing z equals 1/5 r squared. And for this one right here, I'll just solve for z again. Z equals the square root of 36 minus r squared. Okay, so let's write those limits in. I'm going to go from 1/5 r squared up to square root of 36 minus r squared. Okay, now what about r? Okay, well, remember in our intersection piece, right, the circle here, that's the portion that's going to define r and theta for me, because that's where they're converting from x and y, right? X squared plus y squared gives me r squared is equal to 20. So that means that r is going to have to be between 0 and square root of 20. And of course, since it's the whole circle, right, well, theta is just going to be 0 to 2 pi. Okay, so here we go. R is from 0 to square root of 20. And theta is just 0 to 2 pi. Okay? Let's start evaluating, right? Right off the bat, I notice I can get my theta out of the way. There's no theta dependence anywhere else. But the z is connected to the r, so I'm going to have to start there, right? Okay, so integral 0 to 2 pi d theta. Got that one out the way. No dependence there. Integral from 0 to square root of 20. My r passes from this integral. And then I'm doing the antiderivative dz, right? Which is just z. So I'm going to be plugging in top minus bottom into z, which is just going to be this object minus that object, right? So I have r times square root of 36 minus r squared minus 1/5 r squared, like so. Then I still have dr here. Okay? And that makes sense, right? I'm doing top minus bottom to stay inside of the volume of that shape. Okay? So for this piece of the integral right here, it's actually easier if I go ahead and split it into two integrals, right? This integral right here is just going to give me 2 pi. and then I'm going to be times the integral from 0 to square root of 20 of r square root of 36 minus r squared dr. Right? That's the left piece. Minus, bring the 1/5 out, integral from 0 to square root of 20 of r cubed dr. Okay? Now, both of these are pretty straightforward integrals. That's the lovely thing about doing this in this alternate system. Notice most of the integral has already fallen apart, and I haven't had to do anything above a normal substitution even, what I'm about to do here. So if I let u be the 36 minus r squared, then du is going to be negative 2r. So that's what I need here, negative 2r dr, which means I need a negative 1/2 just in front of this integral here. Okay? All right. So let's see, next I'll have 2 pi times, I've got negative 1/2, and then I've got this thing, 36 minus r squared to the 3/2 times 2/3, right? Because of the division by the new power, from 0 to square root of 20. Minus 1/20, right? Because I'm going up to 4, divide by the new power, r to the 4 from 0 to square root of 20. Okay, so now we just got some plugging in to do. We've got 2 pi times the 2/3 times the negative 1/2 right here, right? That's just going to give me negative 1/3 times here, let's not get these parentheses confused. I'll just use a bracket to separate that out. If I plug in square root of 20, right? Square root of 20 squared is 20. 36 minus 20 is 16 to the 3/2. Okay? Minus, if I plug in 0, I've got 36 to the 3/2. Like that. Okay, next, minus 1/20. Plugging in square root of 20 into r to the 4th gives me 20 times 20, or 400, minus 0. Okay? So let's simplify all of these pieces real quick. 16 to the 3/2, that's the square root, which is 4, raised to the 3rd power, which is 64, right? Then minus 36 to the 3/2, which square root is 6 to the 3rd power is 216. Okay? And then over here, I've got 400 divided by 20, right? Which is just going to give me minus 20. Okay. All right. So 216 take away 64 is going to be 152 over 3, right? Negative 152 with this negative though, right? So I've got 2 pi times 152 over 3 minus 20, which is 60 over 3, right? For a total of 92 over 3. Which is 184 pi over 3. Okay? All right. So cylindrical coordinates, right? Much better than the rectangular one. Now, let's do the same integral, but in spherical coordinates, okay? So we still have those same two, right? Which means we have the same intersection, right? They intersect at z equals 4. So keep that in mind. But I want you to take a look at the object again real quick with me, just so we can have a little visual here. So I've got the paraboloid, right? And we've got the sphere on top. Right? The sphere is on top here. In spherical coordinates, you don't have this vertical motion of z to integrate between the two surfaces. Okay? The actual motion of the spherical is usually thought of as the radial one. Spherical does this, right? It expands from the origin. So in my integral, I'm actually going to have to split it into two pieces, because if I draw a line, for example, from the origin outward, I can hit two different surfaces. If I draw a line from here to here, I can strike the paraboloid as I'm leaving the surface. Or if I draw a line somewhere higher up, right, like here, I would strike the top of the sphere. Okay? So while I'm integrating, remember my integrals have to go from something to something, right? It's going to go from 0 in my radial direction, which we'll call rho, right? That's the rho direction. But I have to go from 0 to something, and there's two different somethings that I could happen to hit. So I actually have to separate this into two different instances. Kind of like we did with the cylindrical one later on. You notice we didn't have to, but we chose to split it. We're just going to split this one at the beginning because we kind of have to. It's the only way spherical can describe it. So where's the cutoff? Well, the cutoff is at the intersection, z equals 4. Okay? So we'll need to see the relationship at z equals 4 and how that separates my integration. And really the separation has to be is when am I facing the sphere and when am I facing the paraboloid, right? Well, that's this direction. Has nothing to do with the theta direction going around, okay? That's this. No, it's the phi direction, okay? My rho goes outward in spherical like this. So in order to find the two different surfaces, I'm going to have two different categories of my phi angle coming off of the z, okay? So I'll have from the beginning of phi is at 0 when it's pointing up, all the way down until it hits that intersection, and then that'll be one integral. And then I'll also go, hey, where's that intersection? All the way down to the plane for my phi. So I've actually got to split the phi integral is the one that's actually getting split here. Okay? So I just wanted to give you that visual. So how do I figure out, first of all, what my bounds are and what everything else is, and then how to know where the split is? Well, again, let's convert everything, right? I've got x squared plus y squared plus z squared equals 36. And in spherical, that's just rho squared equals 36, or rho equals 6. So the cap, right, the sphere, easy to write in spherical. Very, very easy, right? Okay, next, in spherical, I'm going to convert the z, the x squared and the y squared. Let's start with z is rho cosine phi, right? And x squared plus y squared is technically still r squared, but r is not one of my spherical coordinates, is it? No, so I can't stop there with the r, right? But don't forget that r is equal to rho sine phi, right? That was in that beginning piece we were talking about, because the way the triangle works with the phi angle, right? Okay, so I need to have something in terms of rho so that I can integrate from the center out to the surface, right? So that's what I'm going to do here. I'm going to solve for rho. 5 rho cosine phi is equal to rho squared sine squared phi. I'm going to divide both sides by rho, which is going to take away 1 from each side. And I'm going to divide both sides by sine squared. So I'll have 5, sine squared phi, I should say. 5 cosine phi over sine squared phi is equal to rho. And that's okay, but let's write it in terms of some easier trig functions. Remember, there's sine phi times sine phi here, so I could split it kind of like this. 5 over sine phi times cosine phi over sine phi, which that's just going to give me 5 cosecant phi times cotangent phi is equal to rho. Okay, so I have my two surfaces in spherical coordinates now. They're rho being functions of our other variables, right? Rho equals 6 and rho equals 5 cosecant phi cotangent phi. Okay, the other thing we need to talk about, remember, is the intersection, right? Where z equals 4. Z equals 4. We need to define this also in spherical coordinates, right? Okay. So z is rho cosine phi, okay? But it's not all of the rho pieces. Remember, we're talking about the circle here is on the surface of the sphere and the paraboloid. So if it's on the surface of the sphere, well, then if I were to draw a line directly to it here, that line would have to be of length 6. It hits the sphere of radius 6, right? All the way around, everywhere in that sphere, if it hits that circle, it's on the sphere, it would have to have that radius of 6. Okay? So instead of rho here, all right, I don't need a variable. I'm not talking about everything inside. I just need the edge. So it's 6 cosine phi equals 4, which tells me cosine phi is equal to 2/3, which this will be important later. That's going to happen when phi is the arc cosine of 2/3. Okay? Now what I'm going to do is I'm going to assign this the letter little a. Okay? For later on when we need to write it, I'll reference it as little a. And then by the time the integrals stuff is done, it'll work out. Okay, so let's set up our volume now. That's our triple integral, right? Over the region dv. And remember, I have to write this as two separate integrals. Okay? So first integral, triple integral, let's do the sphere, right? So rho is going to be the most inside one here, is going to go from the origin 0 out to the sphere, which is 6. Rho equals 6, right? Okay. Next, my theta, right? Theta is just going to go all the way around, okay, from 0 to 2 pi. I don't think there's any other dependencies. Nope. From 0 to 2 pi. And then phi, right? Phi is going to start at 0, because that's phi pointing upward, all the way down until you get to the intersection, which we said that happens when phi is this value that we're calling a. So phi is going to go from 0 to a. And then, of course, if I'm doing dv in spherical, that's rho squared sine phi. D rho we did first, then d theta, then d phi. Okay? Plus my other triple integral here also is going to be the rho squared sine phi d rho d theta d phi. Right? Okay. Now the easy one again is theta. The paraboloid goes all the way around. So my theta is the second piece right here. That's still going to be 0 to 2 pi. Right? We're still going all the way around. Phi, right, is the thing that's rotating this way. We're starting at the intersection and completing through the paraboloid to the plane. So it's going to go from the a value all the way down to the plane at 0. So from a, I'm sorry, not 0, right? This is when it's pi over 2. Right? Phi would be pi over 2, 90 degrees when it actually hits the plane. So it's from a to pi over 2. Now what about the rho? Again, rho integrates from the center outward to the surface. It's just to the paraboloid surface now, right? So I'll be integrating from 0, the origin, out to the paraboloid surface. 5 cosecant phi, cotangent phi. Okay? And now I just need to perform both of these integrals. Okay, so here we go. This one's actually, as you can see, it's already going to be a little nicer, right? Because all of the boundaries on that one are numbers. Let's see if we can make some room here by splitting this down the middle here. Okay. So right here, I'm going to be integrating d rho first. And that's rho squared, right? And then also 0 to 2 pi d theta. Notice there's no other theta dependence. And actually that's true for both of them, right? For both integrals, if I'm integrating d theta, I'm going to get 2 pi in both of them. Because there's no theta dependence anywhere else in either one of those integrals. Okay? So I'm just going to get a big old 2 pi out in the front of both of those. Okay? Integral from 0 to a. And then I'm integrating d rho and then sine phi. Okay? So I've got sine phi, get him out the way. And then that's going to give me 1/3 rho cubed from 0 to 6. And then I've still got my d phi there. Right? All I did was I did the antiderivative of the d rho here. Right? That's just this piece. Okay? So then 6 cubed is 216 minus 0 is 216 still, and then divided by 3. So I've got 2 pi times 216 over 3, which is, what, 72? So I've got 2 pi times 72. And then I've got the integral from 0 to a of just sine phi d phi. Right? Well, integral from 0 to a sine phi d phi, that's a straightforward one, isn't it? 2 times 72, right? There's my 184 pi right there. And then this is going to be negative cosine phi evaluated from 0 to a. Okay? When I plug in a, now here's the fun part. A is the inverse cosine of 2/3, and I'm plugging it into cosine, right? Now think about this. I'm within the normal boundaries of the well-defined arc cosine. I'm not in one of the crazy quadrants. I'm just in quadrant 1 between 0 and pi over 2, right? That angle is somewhere between 0 and pi over 2. And then I'm plugging it back into his own opposite. What am I going to get? I'm going to get 2/3 back again. So I've got 184 pi times negative 2/3 plus, now because of the double negative, right, minus negative, cosine of 0 is 1. Okay, so right here, so far I've gotten 184 pi over 3, right, because 1 minus 2/3 is 1/3. So I've got that side done. Starting to look a little familiar, right, from the last time. Okay, so then this piece right here, that does look a lot familiar from last time. Did I multiply something wrong? Let's double check me real quick. 2 times. I did multiply that wrong. Woo! Man. 2 times 72 is 144. Much better, much better. Good going, good going. Okay. Now, right here, I've already got my 2 pi, right, from the non-dependent integral there. So 2 pi. And then I've still got my integral from a to pi over 2. My sine phi is still there. And then I'm integrating the rho squared d rho, right? So I get my 1/3 rho cubed again. And then that's from 0 to 5 cosecant phi cotangent phi d phi. I know, looks a little messy. Hang on, just bear with me, right? Okay, so I'm pulling the 1/3 out to pi over 3, like this. I'm going to have integral from a to pi over 2 sine phi, and then I've got all of this to the third minus 0 to the third, which is just minus 0, right? So times 125 cosecant cubed phi cotangent cubed phi, right? d phi. Immediately, one of the sine phis reduces the cosecant phi to a squared. Okay? Now, I know you may not be doing a happy dance just yet, but look really closely. What I'm left with is cosecant squared times cotangent to some power. And the derivative of cotangent phi is negative cosecant squared phi. So this is a real quick substitution problem right here. If I just let u equal cotangent phi, then du will be negative cosecant squared phi, d phi. So I can easily wipe this one out as well. I'll factor the 125 out. 125 times 2, right, gives me 250 pi over 3 times, oh, don't forget the negative, right? Negative. It's going to be 1/4 cotangent to the 4th phi. And then that's from a to pi over 2. Almost there, right? Okay. So I've got 250 pi over 3 times. If I plug in pi over 2, right, cotangent of pi over 2, right, think really hard, tangent of pi over 2 is undefined, cotangent of pi over 2, the reciprocal, would have to be 0, right? So I've got 0 minus a negative, so plus 1/4 times whatever cotangent to the 4th of A is. So it's going to be something to the 4th, right? What we need to talk about here is what is cotangent of A, right? We'll come back over here for a second and let's take a look at that. A is the arc cosine of 2/3, which comes from the fact that cosine of phi is 2/3. Well, and that's supposed to be in a quadrant 1 type of situation. So if we have something such that phi is having a cosine of 2/3, that means this side must have been 2 in the triangle, this side must have been 3, and my hypotenuse over here would be the square root of 9 minus 4, 5, right? And therefore my cotangent of A, which happens to be whatever this value is, right? And this shouldn't be phi, this should be A right here. A is whatever that value is, that angle. The cotangent of A is just adjacent over opposite, 2 over square root of 5. So bring that back over here. Cotangent to the 4th of A, 2 over square root of 5. To the 4th, okay? 2 to the 4th is 16, divided by 4 is 4. Square root of 5 to the 4th is 5 times 5, 25. Okay, so I've got 250 pi over 3 times 4 over 25. Right? Okay, so 25 reduces with 250 to leave me with 10, right? So I've got right here 40 pi over 3. And now it's those two integrals added together, right? For a grand total of 184 pi over 3, which is the value we found last time. And yeah, it does feel like this one's a little bit more work. That's just in this situation, right? In this situation, having to split it at the beginning into the two different integrals, and then the integrals had a little bit more trigonometry built in, okay? There are other situations where spherical has an advantage over cylindrical. It really just depends on the kinds of objects that you're dealing with, okay? But I hope this has given you an idea of how you can set up cylindrical and spherical integrals, and how you can actually do either one, compare them, and see which one works better for you in different situations.